Hey everyone. I was watching some of my old YouTube videos from the semester from these sessions, and I realized that it was kind of weird just jumping into our sessions without any real introduction to the video itself. So I'm going to be injecting like these small introductions to let you know what this video is about before you actually dive into it. And so in this session, what we really wanted to do was write functions, first of all, to be able to write a function efficiently by combining for loops and if-else statements and whatnot, to simulate a ballistic trajectory, specifically in this case of a seed. And I thought it would be neat also going back to first principle physics equations to be able to inject whether or not we include drag and see how that affects the flight or the trajectory of objects. And so we'll step through that. A lot of this session was done on a chalkboard. It had to be done, I think, in order to look at the math and in order to look at the variables. And so the camera didn't capture that, but hopefully just looking through the code and listening to some of the things that I was talking about while at the chalkboard should be enough to help guide you through the session. So without further ado, here's how to simulate ballistic drag. So today I really wanted to talk about basic simulations that are based off of first principle physics equations. So I mean, like the physics equations that you learn, like F equals ma, that's pretty much all you need to know with a little bit of like modifications to that in order to make a simulation. But I also want to discuss how you can use, one, how you can implement these simulations, and two, how are they informative? Because I think we could make this code and we could run it and we could turn off air drag or turn on air drag and see what happens. But like actually thinking about how that changes our fundamental like understanding of physics of the physics of biological systems. And actually, I also really wanted to do this specific problem because Steve Vogel, he was on my committee for a bit. He made this program that could simulate projectiles going through the air with and without air drag, but I could never find a copy, and I could never find the equations. And I've always really wanted to remake this, and so that's what we're going to do today. So actually, looking around, because I couldn't find any of the equations, I landed on this site from NASA, and this looks very daunting. All of this is correct, all of this is what you need, but I'm basically going to show you how you can avoid doing the really difficult, or not difficult, but forgotten analytical math and do it in a more numerical way, in a way that makes sense in terms of simulation. But our main goal here, if you want to look through this, it's the derivation's actually pretty smart and it's pretty straightforward. But what we're going to do is we're going to try to find an equation to figure out for each one of these time points the y position of the ball. That's this equation here, and again, this is the like exact analytic solution that we're going to approximate the solution, and then we're also going to figure out the exact x location of the ball over here. And so I'll refer back to this because there is one equation in here that I've never memorized, and it's not intuitive, but it's right there. That's the drag equation. But first of all, I think it'd be good to start talking about what actually we need to do, what goes into the simulation. So what we're doing is we're doing a ballistic drag simulation. Really quickly, can someone tell me what ballistic means?
Like an object is traveling through the air, but it's not producing any thrust or lift.
Yes, so that's very key. So there's no thrust and no lift. And actually, I think it even says it here at the very top. No thrust, constant mass. Flight equations with drag. So ballistic, this basically has to do with like throwing a piece of chalk in the air and seeing where it goes. And there's certain things that we need to know. First of all, what could affect it is how fast it's initially traveling when it leaves, right? So you need some V naught. Also, what you'll need probably is the angle, right? So if I do this versus I throw the chalk across the room, that has a different trajectory. So we'll need some initial theta. And the other thing that's acting on a ballistic projectile, right? Again, what's causing it to come back down is gravity. So I'm going to do that. Great. And with those three things, you could simulate, you could use equations for a basic ballistic projectile. We're going to leave drag out for a second because there's a bunch of things that go into there. But the other thing that I think is important is talking about simulation. Because not only are there physical properties about a projectile going through, but we need to do input certain things into the simulation. One I like doing is T-final. Right? So for example, if I simulate 10 seconds of something flying, that 10 seconds is my endpoint, and that's a very important thing that I need to know. And the other thing that you need to know is your DT, and this is super important. Your DT is, so I could simulate 0 to 10 seconds, and I could do it in intervals of 1 second, and that would give me 10 data points. Or I could have a really high resolution, really small DT, like 0.0001, and it'd be many data points to get from 0 to your T-final. But this is really important just because we're going to be dealing with the dynamics of this. So we're going to not only be dealing with position, but velocity and acceleration. So it's critical that we get the right DT. We want the DT small enough that we don't miss any of those dynamic interactions. For example, if DT is too coarse, we could miss really key moments of a projectile flight. But again, if DT is too small, if there are too many data points, the simulation could take years. So we need to find something that's suitable for that. But if we, for right now, we just ignore drag, these are all of the parameters that we'll need to make this equation. I actually went into, I linked in here this paper about seed dispersal. And while it loads up, I actually went in and I wrote in parameters that they used for this orange jewel bead. So for their V naught, I'll just put this up here so I don't have to get back up here and we can all see it. They had a launch velocity of 1.24 meters per second, a theta of 20 degrees, and of course G is a 9.8 meters per second squared, right? So that means that a seed at t equals 0 is right here, and what happens is that it launches off at 20 degrees, and the original velocity going in this direction is 1.24 meters per second. So that's all that's saying. All right, so let us make a function to try to capture the simulation. And I will pop this out using this button, just so that I get it. All right, so ballistic drag, the first thing we need to do is we need to make a function. What should we call our function? Balsam is what I heard. Was that right? Yes. That's what it's going to be now anyway. All right, so balsam, and we have to assign the a function to it, and this is the basic syntax. So basically what it's saying is whenever R will see the word balsam, it'll know that it's a function. It'll look for certain parameters in here, and then what it'll do is it'll run the code in between the curly brackets. All right, so we already know if we're excluding drag for now, we're going to need some V naught, we're going to need some theta, and we're going to need G. And over there we have two other simulation parameters, T-final or T-final and DT. So one of the first things that we have to do, if you notice that we're going off at an angle, but when you look at the equations, somewhere in there, we're referring to an x and a y. So right off the bat, it's really, it would be good for us to decompose this into some vx naught and some vy naught. Right? So we basically want to separate this 1.24 meters per second into a vertical component and a horizontal component. The way that you do that, if we have degrees, so we have some theta. With R, and actually for most programs, you want to do most of your computations in radians, so you have to convert degrees to radians. I don't know if there's a built-in function, but all you have to do for the conversion factor, if you do dimensional analysis, is you know that 360 degrees is equal to 2 pi radians. So if we take our theta, we can multiply by 2 pi divided by 360, and then we'll get our theta in radians. So that's the first step. We have to convert. So again, we have a theta there. And again, this theta in our script is now referring to this theta up here in the parameters. So whatever value we put up here will populate this theta down here. And what we have to do is we have to multiply it by 2, multiply it by pi, divide it by 360 to get to radians. And what I like to do is, because we'll never really need to refer back to degrees again, we can just overwrite theta doing that. So we can do this calculation with theta and then have the result stored and sent back into theta. So now every time we reference theta, it's not pulling this value, it's pulling this value. Does that make sense? I'm just going to write a note and convert to rads. All right, so then the next step is we want to get the Vx naught, Vy naught. So Vx naught, Vy naught. These are trigonometric relationships. So it would be V naught for, let's see. So for the x component, if your theta is 0, all of your velocity is going to be converted into horizontal velocity. So if cosine of 0 is 1, so that's what we want. So cosine of theta. And we want to multiply these together. So that was not a very good explanation of this, but does that make sense? It might have been a while since you've had to decompose velocities. And for the Vy naught, we can decompose it by doing sine of theta. And again, the way I like to think about it is that if all of your velocity is going vertically, you're going at 90 degrees. And so sine of 90 degrees is 1. So 1 is like 100% of that velocity is going to the y direction. That's how I like to think about that. So what do we do now that we're actually at this part? Come back to the board here. Now we have some Vy, and now we have to think about this, and we have some Vx. Now that we've decomposed these, we can actually think of these as independent problems, which is pretty cool. We can solve for y using our ballistics equations. We can solve for x using our ballistics equations, and at the end we can put them all together to figure out how it moves in the two-dimensional space. And so let's do x first, because I think x is the easiest. When you're dealing with this x velocity, the basic equation that you really want to keep in mind is f net. What does f net equal? Right? So in this case, the f net is equal to the mass times acceleration. Well, maybe we'll start with this because this will be easier to understand. Yes. So another way to think about this is f net is equal to mass times acceleration. It's also equal to the weight, right? The weight of this, right? This has some mass, and the acceleration due to gravity is creating some downward force. But what you can see really quickly is that if f net is equal to ma, f net is equal to weight, and weight is equal to mg, you see that ma is equal to mg, and the m's cancel out, and you just have gravity acting on it. So maybe we will start with this. So we know that the only acceleration that is working on this system at that point is gravity. And actually it's negative gravity. So why don't we do that for a second? Again, the tricky thing right now too is that these equations make sense, everything is good. We're dealing with accelerations. What we'd like to do is go from acceleration to position. That's the main goal. Like, always get that in mind. Our main goal is to figure out how that y value changes. So what we need to actually do is go from acceleration to velocity and then velocity to position. So that's a double integral. And again, the analytical math behind that is right here. But I can't define it. It uses some trigonometric rules and whatnot. So what I'd like to do is do it numerically, do it in somewhat of a simulation sense. And so what you can do, what you can think about is if you know this acceleration, right? We know that a is equal to negative g. What you can do is you can figure out for one time step, you could figure out what the change in velocity is, right? If you know acceleration, this basically tells you the slope of the velocity, how velocity changes. So for one time step, you can get delta v. And then for that same time step, you can extend this and get how delta y changes, right? That is your double integral right there. So that's what we're going to work towards. Okay. So first step is we have to set up the simulation parameters. We basically want a vector saying, time, like these are the times given these time steps. So in order to do that, I just do t is equal to a sequence, and we want to start from 0. We want to go to t final. It should be an equal sign. And here we could do two things. We could put in a length out if we knew how many data points we wanted, or we could do a by, and I think we're going to do by because we have a dt up here, so by dt. So before we go forward, why don't we take a quick check to see if this is working. What I'll do at the end of here is I'll just return t, and I'll copy and paste this into over here. Okay. So what happens now is we can run this. I'm just going to select it all and hit command return. And what it's done is it's created this function. It's done all this stuff into it. So now when we call balsam, it exists. I'm not sure if it'll run because we have to put in all these parameters, but let's just try it anyway. So now when we type in balsam, you can see when I hit tab, those are all the values that we want. So theta, we'll put in 20. Or sorry, for V0 1.24, theta is 20, G is 9.8, T final is 2, and DT we'll just say 1 over 1,000 for now.
So you just put numbers in there. I mean, the function should know the order of the parameters. Can you just say 1.24,
Yes.
20?
Yes. So if you don't put any of these parameters in, it will interpret those numbers in order. For the sake of future readability, I like putting those in there, just because like a year from now you can look at it and know what parameters you used. And especially with more complicated functions, it gets complicated, but yeah, but it would just interpret them in the order that you put them in. And so we do that, and then you'll see that we got a list of numbers. So these are our simulation t's, and in between each t is the difference between those two time steps is dt. So far everything is working okay. All right. So now what we need to do is we need to cycle through all of these t's and try to figure out, one, what are the velocities at those t's, and once we have those velocities, then we have to figure out what are the positions at there. So what we need to do is we can do it using a for loop, and it almost looks like a function. It's the same sort of thing. You have a for here, open close parentheses, open close curly brackets, and I'll just type this out and explain it. For I in 1 to length t. This is a very typical way that you'd run a for loop. Basically what it's saying is that you're having this temporary variable I that will exist somewhere within these curly brackets, and it'll run it'll run whatever in the curly brackets once, replacing I with 1, and then actually 1 to length t is it goes 1, 2, 3, 4, 5, 6 until I guess 1,000 points here or so. And so each time we can access a different t value. And so our goal is to figure out, just write the goals here, get velocity at each time step. And then from that, we want to get position at each time step. So let's deal with the y's first. We know here that the acceleration is going to be negative g, right? So our velocity at a time step is going to be equal to, I'll just type it out, the previous velocity plus, and I'm just putting this up here so that we can look at it, times dt, right? So the way to think about this is if you have some velocity previously and it's accelerating for that small of a time step, if you multiply the acceleration and the time step together, you basically, if you just look at dimensional analysis, right? If you have acceleration is meters per second squared, and you multiply it by dt, which is some seconds, you will get some instantaneous meters per second. So this is the velocity that, the change in velocity that has occurred within this time step. And so we know right here that the acceleration is going to be negative g, so we can just do minus g. And now this thing about v previous, we have to set this up because right now we don't have anything to record our velocity at each time step. So I like to do something, we'll call it like vy's, right? These are our velocities in the y direction, and s because they're multiple of them. And I'll just repeat, let's do the initial velocity, v y naught, and I'll repeat it for the length of t. So what this has just done is it's set up right now this thing called vy's, and initially it's set to the initial y velocity, and this length t just means that there are as many of these numbers as there are time steps, right? And so what we can do is to grab v previous is we can just do vy's and grab a subset like that using a square bracket, and we can do I minus 1, right? So if I is the time step we're trying to solve for, I minus 1 is the previous one, this gets into a weird error because right now we're going from 1 to length. So if you do 1 minus 1, you get 0, and R is not going to understand that, so we can just fix that by changing that to 2. And we can do that because our first velocity at that time step is going to be vy naught, or vy 0. And that's set to repeat. So if we don't change it, that's what it will be. All right, so that is how we get the vy's. We can do the same thing for position. We can do xy's. And in this case, we're going to repeat. Since we start at 0, 0, let's start at the origin. We can do that at length t. And in this case, what we haven't done yet is we haven't stored this anywhere, and that's what we want to do. So we want to put this into the previous time, the current time step of vy's. So we can do that by vy's square bracket I. Right. So this is going to start at 2. It's going to pull the second value of vy's, or actually it's going to pull 2 minus 1. So it's going to get the first one, figure out how much of the velocity has changed within our time step, and then set that as the second value of vy's, and it's going to do that for the whole thing, for every time step. Is that good so far?
Yeah,
Where is it?
X, Y,
Oh, I see it. Cool. So I'm going to do that. And so we can do the same thing here, our x. So I'm going to model this after this top equation here, this top line of code. But x, y's, I, square bracket I. We're going to set that as our previous. Here? Yeah, so maybe x is not the right. So you know what I'm going to do? I'm going to call this maybe like y is instantaneous. Just change it to that. Because I'm using x as a to represent position, but it's confusing because there's a x position and a y position. So then I'll just change it to y instantaneous. That's fine. So what we want to do is we want to pull, just like over here, the previous the previous value. So we have I minus 1 here. And much like over here, we did acceleration times dt. What we want to do here is now we want to do velocity times dt. So we have to pull our current velocity, which we stored over there. So we'll do that, and we'll multiply that by dt. And again, this is essentially doing the same thing as we're doing before, except we're using this value that we calculated previously. And that's how you get your estimation of the double integral. So now we can actually go to the x case. And the x case is actually really easy because, well, once you throw an object across the room, if you ignore drag, there are no other forces acting on it. So its acceleration is going to be 0, right? So we can just pretty much go up here and do x, and we have to do the same sort of thing. I'm just going to copy and paste these just to save a little time. And now instead of velocity in the y, velocity in the x. And what I'm going to do is I'm going to say acceleration is equal to 0 and change this g to an a. Right. There's a reason I'm doing this that it becomes important a little bit once we talk about drag, but just know that by setting a to 0 and doing a times dt, it's like this doesn't exist at all, right? So our horizontal velocity doesn't change. We're adding nothing to it every single time. But this is just to set up the code for the drag component. And here I'm going to do x is instantaneous, x the previous one plus vxs dt. Yep. So then we have to set them up here. So these are vx's. Repeat vx naught, and then y inst. So this is x's inst. So that takes care of the entire simulation. Just because I'm getting, we haven't tested any of this out, and I'm curious whether or not this will work. I'm just going to jump ahead to the to plot it. I'm just going to say x is equal to x inst, y is equal to y inst, and that should be enough. So I will copy that, and I will also run it to make sure I get no errors. I don't, and I'll paste it over here. So now I'm just going to hit up until we get back to our balsam line code right there. And I'm going to hit run and see if that worked. Okay. I'm missing an underscore somewhere. No, it must be up here somewhere. It's not found. Oh wait. Yeah. I was looking at the wrong code. There we go.
It's
XS,
XS.
XS instead of Y.
Yeah, if I had been smart, I would have come up with better names for these, but. Alright, copy that, run that, no errors. And run. Great. So that is our seed. And you'll see the thing that I don't like about this too is that it plots every point, so it goes way negative. If we want to bound this to 0, what we can do is we could set a, again, this is the wrong code. Over here, in my plot, I'm just going to set a y-lim to be 0. So the lower limit of our y-axis is going to be 0, and the upper limit I'm just going to set as max y-inst. Copy, run, see if it works before I paste it. There we go. So a nice little thing. So maybe our t final was too long, so the good thing is we can go in here and we can change our t to 0.2, see what that does. There we go. That looks like a nice ballistic trajectory. So I'm actually going to show you another trick too, for those of you who want to add this in. I don't like having to put these in every single time because I feel like this, I mainly want this to simulate this seed. So what you can do is you can set default parameters so that if you don't fill them in, they'll automatically have a value, right? So if you just do equals 1/1000, now if you leave out dt, it'll automatically just assume that your dt is 1/1000. You can do that over here with final. I'll just make that 0.2, I guess. G, especially G, right? Unless you're gonna simulate like not on the Earth, like you could keep that. We can do 1.24. I believe those are the values in there.
Should G be negative that way, or?
No, because we take care of that down here. And so I'm just gonna run that. So now you'll see if I just do balsam, right, without any parameters in there. It's actually cool. I didn't know RStudio did this. It gives you a little indication of what your default parameters are. You get that, which is great. So the reason why we did fnet, and we'll do it specifically in the y direction. When we didn't have drag, it was just equal to a downward force due to weight. But what happens is that if you do incorporate drag effects, then there's also going to be another force here that resists this, especially when you're rising up, going down, what have you. So if I were to take this book and I were to toss it up, the weight will have a force going downwards, and the drag in this case will also have a force going downwards, right? So then you have this negative drag force. So in this case, our MA is equal to negative MG minus what this drag force is. So if you look back on that website, drag force over here, that's the equation for drag force. Drag is equal to, it's 1/2 times the coefficient of drag times rho times area times velocity squared. So some coefficient that has to do with the object and Reynolds number. We can talk about that later if you want. But some coefficient times the density of the fluid that you're moving through times the area, right? So if you have a giant area versus a small area, that's going to affect how much drag you have, times the velocity squared. So there's a velocity plays a big part in how much drag there is, and then divided by 2. This is the drag force equation. So if we put that over there, CD rho A squared over 2. Our equation is set up right now in terms of A, so I'd like to get A isolated by itself, and to do that you just cancel out these m's and put an m over here. So you divide this by m, divide that by m, divide that by m. So your final acceleration equation for the y is not just negative g, but it's negative g minus the coefficient of drag times rho times a v squared over 2. Right. So these are all the drag things that we need. We need the coefficient of drag. We need rho. We need area. V squared is something we calculate. That's not a parameter, but we need mass. So let's start off with the easy ones. I don't have this number because I wrote it somewhere. Rho for air is 1.225, and that's kilograms per meters cubed. The area of the seed from that paper is 1.2. No. It's 5.99 times 10 to the minus 6, meters squared, and mass here is 10.1 times 10 to the minus 6 kilograms. So the only thing left is this coefficient of drag, and this is the weirdest part of it. You have to really get this experimentally if you want a really good model. But if you just want to have some estimate, these are the drag coefficients for regularly shaped objects, specifically with moving in fluids with a Reynolds number of approximately 10 to the 4. This is a good place to start. The paper actually uses the coefficient of drag of 0.47 of a sphere. They modeled the seed as a sphere. So I think that's a good place to start. So what we can do is, right off the bat, we can just plug these into our parameters so we don't have to worry about them. I'm just going to put them on a separate line to make it clear. I'm going to have a coefficient of drag, 0.47. Going to have rho, 1.225. We're going to have an area, which is 5.99. times 10 to the minus 6, I believe. Yep. I'm going to have mass, which is equal to 10.1 times 10, again, to the minus 6. Right. And that's just another thing to know, that you could split these up on different lines visually however you want. R's not going to care. So if we look back here, this is the part that we need to update, right? A is equal. So in the first part, we just set A is equal to G, and you can see that over here. I'm actually going to modify it a bit to make it more general, right? So instead of like as we did over here, where A equals 0, I'll say A is equal to negative G, and I'll just replace this negative G with an A, just to make it more general. Everyone see that sleight of hand there? And I'm going to add one more parameter in here, actually, which is drag is equal to true. Why I'm doing this is we can have this drag function. We can set it to true, we can set it to false, but we can easily, just with this true or false thing in our function, turn drag on or off. I think it's pretty convenient. And so in this case for the y, this is the equation that will give us acceleration when there's no drag. So what we can say is that if drag, and so right now, so what you'd want to do is this is equal to false, right? So now we have, if drag is equal to false, this is A. And I want to do curly brackets. around. And the reason I want to do this is because I want to add an else, right? So in the case where drag is true, right, this doesn't get run, now we can put in some equation for acceleration that incorporates drag. And in our case, it's going to be drag is equal, or acceleration is equal to negative g minus, and I'm going to put, let's see, CD times rho times a times. Now here it's expecting a v squared. And what we need to do is get the velocity, the previous velocity. So in this case, it would be vy's, again, I minus 1, because we want to grab the previous velocity. Does everyone see what this is doing? How we added a little switch here to say if there's no drag, a is equal just to negative g. Otherwise, a is equal to negative g minus this value. Oh, and we have to divide this by 2m. Almost forgot that. So we have to do the same thing for x. Funny thing with x is that the only difference between the acceleration in the y and the x is that if you're dealing with x, there's no effect of gravity, so it's just the negative force of drag. So we can just copy and paste that and put it down on x. So again, I'm going to do if drag is false, our acceleration is going to be 0. Else, our acceleration is going to equal to this. And we just, that little change, we now have a switch. Because we wrote this very generally, we don't need to change any of the code down here because it's all referring to this acceleration that we set up there and up there. And I'm going to do, well...
And because it's a loop, it doesn't matter that we're using a twice for different things.
Mm-hmm. Right. So in this case, this a will be plugged in down here, but that a gets overridden again, and then the a's down here referred up here. I mean, if you want to split it up into ax and ay, I mean, that's better in my opinion, but it doesn't change what the code does. So I am going to run it and see. So here I have balsam, and I'm just going to here, just so we know specifically, drag is equal to true. We do drag is equal to false. They look very similar, but things are changing. I'm just going to interrupt the live feed that we had from our last session because I wanted to talk really quickly about some of the mistakes that I made and some of the things that I said that were incorrect in our last session. I just wanted to make sure that everyone had the right code if you're coming back to watch this video to get a refresher or to make your own version of this code. And basically, one of the first things that I noticed when I was rewatching the video was when I copied and pasted some information. I believe I copied and pasted these, the y velocities and the y positions. I just copy and paste them down into the x. Just make sure that basically when you do that, that you're now referring to the x position and not the y. So if I think before last time these were y's, so just make sure that those are x's. Also make sure that these down here are x's. So that's the first thing. And the other thing was there was a bit of confusion on my part about which velocities that we should be using in our calculation of drag. I remember I mentioned that possibly that we should be using terminal velocity all the time, but as I thought about it more, that's actually incorrect. You want to be using the velocity that the object is experiencing at any given time, either in the x direction or in the y direction. And so the original code that we had was correct. You should be referring to the previous velocity, the velocity of the previous time step in both the x and the y up here. All right, so those are just minor things, basically saying that we had it right the first time. And the other thing that I wanted to mention that I cut off from the end of this video is this last little code down here, where I add a switch to whether or not you could plot or add lines on top of a plot, and this is really important. So let me show you what it does first, and then I'll go through the code and make sure that we understand what's going on. Well, if you notice, I'll just run this, load this into my terminal, and now I have something that's called balsam. And let's just first of all just turn drag off, so drag is false, and we're keeping all the same parameters that we use for the seed, just so that we can get a plot and see what that looks like. There we go. I'm actually going to change the time on this just to scrunch it a little bit. I believe that if I set t final to 0.1, things should look a little better. There, that looks a little better. And so remember, this that we just plotted, we said drag was false, so drag is off. Now, what I ended up doing also is allowing you to change this quickly to true, but also I added this parameter called add, and if you turn add into true, instead of erasing the entire plot, you could put your data on top of the existing plot. So it's a really easy way to compare with drag, without drag. So if we run that really quickly, you'll see that now we have this dotted line that pops up just right there. And this dotted line was added. This dotted line is including drag in the calculation, and including it in the right way. And I also made it a dotted line, so you could really quickly differentiate between lines that you start with and lines that you add on top. Primarily because I'm interested in looking at the effect of with drag and without drag. And what you can see is that when you add drag, right, you don't quite get, you get close, but you don't quite get to the same height, and you don't get quite to the same maximum horizontal distance. And that's what you would expect from drag effects, right? You'd expect some of that energy to not be in the system. And so let's go quickly over the code. I added this add equals false over here, which is what allowed me to add something on top. I just said add equals false so that if you completely forget about it, it assumes that you don't want to add something, you want to create a new plot. But if you see at the very bottom here, I have this if add line. So let's first start with the else, because I think that's very simple. So if not add, or if add equals false, in this case, it's our standard plot with our x equals the x's instantaneous and our y is equal to y's instantaneous. We set the y lim just like we did last time, and I just added this type L just so that we could see lines instead of dots. Basically, this defaults to type is equal to p, and those p for points, L for lines. It's just, I think it looks much cleaner this way, so I like to keep it with L. But you'll notice now that if we actually trigger this, add here, instead of doing the plot function, it does the lines function. And it does the same thing. X is instantaneous, Y is instantaneous, and the only thing I did here differently is I put L2Y equals 2. That stands for line type, and 2 is a dashed line. I believe 3 is like a dotted line, and a 4 is like a dashed dotted line. And I think there's only 4 of them, maybe 5. But anyway, this is just an easy way for me to signify that I want a different line type. If I wanted to also as well, I could even change the color. I do this often. Say that we just change this to red. And so now if I run this code, again, I'll run balsam for our seed, and I'll say plot add is equal to false. And we'll just be sure that our drag is turned off. So drag is equal to false. We run that, we get our plot. Oh yeah, and let's change our t final to 0.1. Just make it look a little spread out. Cool. So now I'm going to do the same thing, except I'm going to turn drag on, and I'm also going to turn add on, so we're putting it right on top. And now you should see a dotted red line. So that's just another way to deal with that. And I just wanted to mention, while I had your attention, I put in this little word problem at the very end of last week's script, and you can see that this is a problem of a baseball, with a radius, some mass, some coefficient of drag, and it's being thrown or hit into the air. And I thought it was just kind of cool. We can use the same function here. I just put in the different parameters to make it applicable to a baseball versus a seed. So I just wanted to show you what that looks like. Here's a trajectory of a baseball. You can see that it goes 250 meters in the horizontal direction, and a little north of 40 meters in the vertical direction. That's without drag. But here you can see that I turn drag on, I also turn add on, and when I run that, you can see that the effective drag is huge on a baseball. And so this just, I thought it'd be neat to see, just because we were simulating a seed that didn't seem to have very many drag effects, but comparing that to a baseball that has huge drag effects. And again, all these things are relative. So yeah, I hope that was helpful. I hope that this gave you some idea of things that you could do in your own codes, ways that you can perform your own simulations. And really, like, this is the first time we've used these true-false switches to allow you to access different parts of your code. I use those types of tricks on a daily basis. So, yep. I don't have much else to say, but yep, I hope that was helpful.